For section 2.6, we're going to be looking at compound inequalities. We're going to be solving, graphing, and writing compound inequalities in interval notation. Now, what is a compound inequality, you might be asking? A compound inequality is an inequality with more than one inequality in that problem. There are two types of compound inequalities that we're going to focus on: and inequalities and or inequalities. Let's look at and inequalities first. And inequalities are intersection inequalities. The only part of the graph that we accept is where the shading overlaps, or, for example, where both of the inequalities share numbers. Now, the way that we're used to seeing and inequalities is like this problem below, where the x, along with an operation, or maybe more than one operation, is in the middle, and we have our extremes out on both ends. So in this case, what you want to do is get the x by itself in the middle. Now, to do that, you actually have to subtract that 3 over both inequality symbols. You've got to move it to the right and you've got to move it to the left, since we've got two inequalities here, giving us the inequality of -8 is less than x is less than or equal to 7. Now, as we learned previously, if you would graph that on a number line, remember you want your smallest number to the left and your biggest number to the right. It would be graphed something similar to this. And if we were writing it in interval notation, it would be all the numbers between -8 and 7. Now, I want to take a minute and show you a different type of problem. This is also an and problem. The reason I know that is because of the and symbol in between. On our previous problem, the and problem that we're used to seeing is when the x is in the middle and the extremities are on the outsides. You can see and inequalities where they're written as two separate problems, and since they're written as two separate problems, we have to solve them as two separate problems. So in this case, I'm going to put my x's together by using my inverse property, giving me -2x less than or equal to 8. Divide by -2. Now I'm dividing by a -2, so I'm going to have to flip that sign. I've got x is greater than or equal to a -4. I'm going to come over here, I'm going to solve this one as a separate problem. So I'm going to divide by 3, divide by 3. I'm dividing by a +3, so there's no need to flip my sign. I've got x is greater than or equal to -3. Well, let's take a minute and graph that, because we need to graph and write this in interval notation. Remember, an and problem is a problem in which you take only where the shadings overlap. Well, if I graph this one, it says greater than or equal to -4. So greater than or equal to -4 is going to head in this direction. If I graph greater than or equal to -3, greater than or equal to -3 is also going to go in that direction. Now, to us, this looks very silly. We're not used to seeing and inequalities graphed like this. Most of our and inequalities overlap right in the middle. Well, remember, since we only take where the shadings overlap, this portion of the graph is the only part of our graph that is the solution. So as I'm writing this in interval notation, my answer is only every number from -3 to infinity. In other words, only any number between -3 and infinity, when plugged into both of these, will actually satisfy both inequalities. If you would plug in a number in between -4 and -3, one of these would fail, as well as if you plugged in anything less than -4. One of these would fail. These numbers are the only case in which both of them would pass, or both would satisfy the solution. All right, let's look at another problem. This also, again, is an and inequality due to the and sign in between. So I know that when I graph this, I'm only going to be taking the portions of the graph where they overlap. As I'm solving this, the first thing I'm going to do is using my inverse property. I'm going to add that 2 over, give me a 7. Then I'm going to divide by a -3. Now, the minute I divide by that negative, I've got to flip my sign, giving me x is greater than -7/3. Coming over here, I'm going to use my inverse property. I'm going to divide by a +5, meaning I'm not going to flip my sign, and I've got x is less than or equal to a -4. As we come down to graph that on a number line, -4 is less than -7/3, so it will go to the left of the number line. And let's graph these separately. This reads x is greater than -7/3. This particular inequality reads x is less than or equal to -4. Now, I've got a little bit of a problem here. This is an and inequality. I can only take the portions of graph that overlap. In this case, neither of them overlap. Nothing overlaps. When that happens, your answer is no solution. There is no solution to this particular problem. In other words, there is no number that when you plug them into both of these will it work. numbers might work in this, or they might work here, but you won't find a number that actually satisfies both of them at the same time, giving you no solution as your answer. Now let's look at our second type of compound inequality. The second compound inequality that we see are OR inequalities. OR inequalities are union inequalities, and what that means is whether they overlap or not doesn't matter. We accept all of the graph, everything. Anything that's graphed works. Now typically we are used to seeing OR inequalities that look similar to this. The reason I know it's an OR inequality is because there's an OR sign in between, and as we solve this, let's look at our solution. So the first thing I'm going to do is, using my inverse property, subtract that 4x over. Now I haven't divided by a negative yet. Here I go. Now I'm dividing by a negative, so I'm going to need to flip that sign. And this reads x is less than 1. Over here, dividing by a negative right away is going to have me flip my sign, giving me x is greater than or equal to 3. When we go down here on our number line and we graph that, we've got a 1, we've got a 3, x is greater than or equal to 3 would graph this way, x is less than 1 would graph this way. We're used to seeing this type of OR graph. We're used to seeing this, and we accept all of it. We don't care that it doesn't overlap anywhere because it's an OR inequality. What we're not used to seeing is how to write this in interval notation. When you're writing this in interval notation, what you need to do is you first need to represent this portion of numbers. Then we use a U, or a union sign, since ORs are unions, and then we represent this set of numbers. It looks similar to this. In this case, x can be anything from negative infinity to 1. Union, or x can be anything from 3 to positive infinity. So what that U does in the middle is it represents this blank space. So I'm saying x can be anything in between negative and 1, or it can be anything from 3 up. Let's take a look at a different type of problem. So we got an OR inequality again. Once again, I know it's an OR inequality because of the word OR, which means no matter what this graph looks like, I'm going to take every number. So right over here, I'm going to use my inverse property. I'm going to divide by that negative 4, and since I'm dividing by that negative 4, I'm going to flip my sign. Over here, I'm actually dividing by a positive 5, and since I'm dividing by a positive 5, I am not going to flip my sign. Now, as we graph this and prepare to write it in interval notation, remember we want the smaller number to go to the left and the bigger number to go to the right. Negative 2 is less than negative 3, so it'll go to the left. This reads x is less than or equal to negative 2. This second graph over here reads x is less than or equal to negative 3. Now, in this case, they're both going in the same direction. Now, if this was an AND inequality, we would only be concerned where they overlap, but it's not. It's an OR inequality. So we're going to take the entire graph as our answer, making my possible solution anything up to negative 2. So the set of numbers that would work in either of these graphs would be the set of numbers between negative infinity all the way up to negative 2. Remember, we don't care that the graph doesn't overlap. Now I want to take a minute and look at another type of problem here. This is an OR inequality because of the OR in the middle. So I'm going to go ahead and solve both of these separately. The first thing I'm going to do is divide by that negative 2, which will flip my sign and make that x is less than a negative 3. Over here I'm going to divide by positive 4, meaning I'm not going to flip my sign. I'm going to get x is greater than a negative 5. Now as I prepare to graph this on my number line, remember you want your smaller number to the left and your larger number to the right. The problem over here reads x is less than a negative 3, and less than a negative 3 is represented by doing that. This problem over here reads x is greater than a negative 5. So if I graph x is greater than negative 5, it's going to graph over here to the right. Now if this was an OR problem, we would only be concerned with what's in the middle where it overlaps. But this is not an AND problem, this is an OR problem. With an OR problem, we take everything. In other words, we care about the entire graph. In this case, everything on the graph is going to work, and therefore my answer is negative infinity all the way to positive infinity. All of the numbers work.